This lecture will introduce long memory neurons. At the end of this lecture, you'll see why long memory neurons are better and what kind of state they store. We've spoken earlier of the fact that recurrent neural networks, which are unrolled very far back in time to learn the distant past, tend to be very deep. This in turn means that they're especially prone to problems of deep neural networks, such as vanishing and exploding gradients. A layer of the recurrent neural network is made up of a group of neurons which are together called the memory cell. One way to solve this problem is to have your memory cell somehow store long term memory. Here is what a simple feed forward neuron looks like. It takes in the input X and produces a scalar output Y. As the simplest recurrent neuron, on the other hand, feeds the output Y at time instance t minus 1 back to the input at time instance t. So far, we've said that the state maintained by the simplest recurrent neuron is basically the previous output that has been fed back to the input. The output at time t depends on the output at time t minus 1. And this output is the state within a recurrent neuron. And this is what the neuron uses to remember the past. This is the memory of the neuron. In order for the neuron to remember long term state, we can make the internal memory of the neuron a little more sophisticated. In such a case, you can imagine that it's not just the previous time instance's output that is fed back to the input, it is this long term state depicted by H that is fed back to the input of the recurrent neuron. Now that we know what it is we have to do to allow us to train extremely deep recurrent neural networks, we can restate the problem. We want long memory recurrent neural networks, and this we can achieve by increasing the amount of state within a single neuron. The net effect of this operation is to increase the memory of the neuron and allow it to remember events from the distant past. Now, in order to increase the memory of the neuron, we need two kinds of state that the neuron holds: long term state, that is represented by C, and short term state represented by H. So, we need to know important events from the distant past and important events from the recent past. Once the problem was restated in this manner, data scientists and researchers turned their attention to adding memory to the recurrent neuron. And they found that long memory neurons which hold additional state, have several advantages when used in RNNs. The advantages of these long memory neurons manifest themselves in both phases in which your machine learning model might operate. There are advantages in training as well as advantages in prediction. During the training process, you'll find that training runs much faster with long memory neurons. That's because even very deep neural networks will largely have their vanishing and exploding gradients problem mitigated. The gradients are smoother and nicer. They can be propagated backwards through the layers. The model will converge faster. In the case of prediction, there is a huge advantage because we don't need to truncate your back propagation through time, truncate the time period over which you learn the data in order to make prediction easier. Predictions from your RNN improves when you don't truncate the past sequence that you feed into it. In order to consider the advantages of long memory neurons, we first have to consider the disadvantages of using truncated backpropagation through time to train your neural network. When we try to learn the distant past, vanishing and exploding gradients are very likely to occur in your recurrent neural network. The neural network is deep, there are many layers that you have to train, and you'll find that training such a deep RNN also takes forever. It takes a long time because there are many weights and biases that have to be tweaked. We saw that one of the options to mitigate such a situation was to use truncated backpropagation through time. Truncated BPTT simply involves you truncating the input sequence that you feed into your recurrent neural network. So instead of focusing on the distant past, you only focus on an aggregation of events from the distant past or on recent events. To consider a specific example, if you were to predict stock movement for tomorrow, you could choose to use only last week's data. Even if you have the data for before that, you won't use the data for last year at all because that will result in a very deep recurrent neural network. Or you might try some variation. You do want to use last year's data, but you'll use daily data for the last week and monthly data before that. But what you're actually doing when you try truncated BPTT is getting around the problem. You're not actually solving the problem. And it has been shown in real world scenarios that truncated BPTT can kill prediction performance. This is because your problem statement might have a solution which relies on events from the distant past. What if the movement of stock tomorrow depends on how the stock moved on the last quarter ending date or even a year ago? What if these movements are seasonal? You won't be able to capture this using a truncated BPTT. Long memory neurons store within them additional state. This state is made up of two components. One is long term state, which is stored over a long period of time, and another is short term state, stored for a shorter length of time.